Hey everybody, welcome to video note 6.3. Three main topics: limiting reactants, excess reactants, percent yield, and percent yield. Here are the objectives that we're going to cover in this video. Please read chapter 9 in the book and look through sections 4 and 5. And after you're done with the video notes, try self-check problem 9.7 from page 258. Okay, remember tricycles? We need something for bears to ride on, so we have to make tricycles. So here's the balanced equation for making tricycles. If I have 6 wheels and 12 frames, I have 2 amounts of reactants. So I got to figure out which one of these 2 reactants gets used up and how many tricycles I can get. So I would say, well, if I have 6 wheels, then I find out I need 3 wheels for each tricycle, and I'll be able to make 2 whole tricycles. Woo! If I have 12 frames, then I find out it takes 1 frame for every 1 tricycle. I'm going to be able to make 12 tricycles. But wait, I'll never get to 12 tricycles. Why not? Because my wheels will run out after I make 2 tricycles. So what does this tell us? It tells us that the 6 wheels limits how many tricycles we can get. How many tricycles we get. So wheels in this problem are what we call a limiting reactant. Right? The other thing we can find out is that we'll only get 2 tricycles, so the limiting reactant tells us how much product we can get. And we can find out that if I use up enough wheels to make 2 tricycles, I can find out that if I had 6 wheels, I'm going to use up 3 wheels for any time I use up 1 frame. So I'll only use up 2 frames. If I had 12 frames to start with, minus 2 frames get used up, then I'm going to have 10 frames excess or left over. Okay. So those are the main ideas, but now we're going to apply it to chemistry. How does that work with a chemical equation instead of a tricycle? So, okay, definition time. A limiting reactant is a reactant that will get used up first in a chemical reaction. It is also the reactant that controls how much product you're going to get. Just like the wheels told us we're getting 2 tricycles, a limiting reactant will tell us how much product we should be able to get. An excess reactant is left over when the reaction is done. So here's a diagram for this balanced equation. The N2 is green and the H2 is white. So let's see what we need. For every time we use up 1 N2, all right, we're going to use up 3 H2s. 1, 2, 3. All right. We use up 1 N2, we're going to use up 3 H2s. 1, 2, 3. All right. And so using all of that, we get 4 NH3 molecules. But what do you notice? You notice that 1 N2 doesn't get used up. So the H2 is the limiting reactant. The N2 is the excess reactant. We're going to be able to get 4 NH3 molecules based on the limiting reactant, and 1 N2 will be left over. I want you to do that same kind of thing with this diagram, and we'll talk about that in class. But the important thing on this slide is that you could practice that, and that for calculating, when we do calculating, we have to use the limiting reactant for all the calculations once you figure out that limiting reactant. And then we have to do a limiting reactant problem whenever there's 2 amounts of reactants given in the problem. Hey, check it out. It's a problem. It says 20 grams of Hg, that's a reactant, 5 grams of O2, that's a reactant. What kind of problem do we have to do here? A limiting reactant problem. Our goal is to figure out how much HGO can form, all right? And we have to state the limiting and excess reactant. So let's get busy doing some stuff. We have 20 grams of mercury, and there's 200.1659 grams of mercury. I got that from the periodic table for every 1 mole of mercury. All right, what does that tell us? That tells us how many moles of this we have. But in order to figure out how much of product we can get, we have to change those moles into these moles, moles of Hg into moles of Hg. Since it wants the answer in grams, we don't stop there. Although that would help, we could stop there if we wanted limiting reactant only, but we want to know grams of product. Okay, How do I get numbers when it's moles to moles? Well, coefficients. Okay, coefficients. And then moles to grams, 1 mole equals mass from the periodic table, 216.5. Okay. When I say goodbye to those and those and those, I say hello to HGO, grams of HGO. All right, math-wise, I get 21.60 grams of mercury oxide. Not done yet because I still have to figure out which one of these reactants is limiting. So I put down 32 grams of O2. Thank you, periodic table, 1 mole of O2. Now I can change oxygen into mercury oxide. Moles of oxygen, moles of HGO. All right, and then, boom, I can change moles of HGO into grams of HGO so that I can compare some stuff. All right, moles of HGO is 2. Boom, moles of oxygen is 1. Grams and moles, 1 goes with moles, and grams comes from periodic table, 216.5. Okay, when I do the goodbyes, thanks for playing, it's been fun, nice to see you. I say hello to grams of HGO. This time, when I calculate, I get 67.68. What does this all mean? Well, it means that if all my mercury gets used up, I'll get 21 grams of mercury oxide to come out if everything goes perfectly. This says if I use 5 grams of oxygen, I should get 67.68 grams of mercury oxide. But wait, there's no way I'll ever get this much because it looks like my mercury will run out after 21 grams of mercury oxide forms. So, information. Hg is the limiting reactant because it gives less product, meaning it's going to run out before all the oxygen does. Oxygen is the excess reactant because it gives more product than Hg can give. All right? So that means there's going to be some left over. So we answered this part, state the limiting and the excess. Now we have to figure out the maximum amount of HGO form. Well, this is the most we can get, the most HGO we can get, because you can't get more once the mercury runs out. Once the mercury is gone, folks, you're not getting any more HGO. Just like once the wheels are gone, you can't get any more tricycles. Okay, so that's how you calculate the most product you can get out. And that's how you decide what the limiting and excess reactant are. But what if someone wanted to know how much leftover there was? So we need to find out the extra amount of leftover, so maybe we could recycle or use it so that we don't waste it. All right. So to find out how much excess is left over, start with the limiting reactant, convert it to the excess reactant, and that'll tell you how much you need. That'll tell you how much excess reactant will get used up, and then subtract, and you have what's left over. Okay. Hey, there's a hippo that's telling us it's all good in the hood. All right, new problem. 90 grams of FeCl3 and 52 grams of H2S. Oh, look, reactant. So before I even go on, I know this is a limiting reactant problem because I have a mass of 2 reactants. Question says, what is the limiting reactant? I already knew I had to find that. What is the mass of HCl produced? Oh, I got to figure out what's the most that can come out, and then what mass of excess reactant remains. Okay, so how much leftover is there? So 90.0 grams of FeCl2. Grams of FeCl3. I said 2, I meant 3. Right, FeCl3. And then, once it's moles of one kind, thank you, balanced equation, we can change it into moles of another kind. Why did I pick HCl? The reason I picked HCl is because the problem asked about HCl. And the problem doesn't ask about moles of HCl, it asks about grams of HCl, so I'm going all the way to grams. Alright, oh, you use this Harbin, you didn't put any numbers in those conversion factors yet. They already didn't. And I'm just going to set up all my conversions first. So, remember, change grams to moles. You'll be okay doing that. Now that I have moles, I can change one kind of mole to another. Okay. And then I can change moles of the new kind, HCl, to grams of HCl. Okay, so here's what's going on. Anytime you see moles of one kind to grams of the same stuff, One goes with moles, and the periodic table is for grams. 162.20. Okay. Now I look for coefficients. There's a 6 and it's 2. Right. Hey, look, it's grams and moles again, and it's HCl. So 1 equals 36.46. Thank you, periodic table. All right, goodbye grams, goodbye moles, goodbye other moles. Hello, HCl grams. All right. Calculate it, and you get 60.69 grams. Okay. Look, it's moles and grams of the same substance. I gotta go to the periodic table. 34.19. Moles and moles, coefficients. So 6 and 3. All right. Grams and moles, periodic table. All right. So goodbye, goodbye, goodbye. Hello, grams of HCl. And then math-wise, I get 111.23. Okay. So what does this mean? It means two things. It means that FeCl3 is the limiting reactant. Why? Because it gives less product. It also means that H2S is excess. Right? So we found the limiting reactant. And when we found the limiting reactant, we found out that this is the most HCl we can get. Because the most we can get comes from the limiting reactant. Okay. Now we can do the excess reactant one. So we know the limiting reactant is the 90.0 grams of FeCl. So now if we change those grams of FeCl3 into moles of FeCl3, and then we're going to change the moles of FeCl3 into moles of H2S, the other reactant, and then moles of H2S into grams of H2S. All right, so let's do it. 1 mole periodic table, 162.20. Moles to moles coefficients, 3 to 2. And then moles to grams, 1 mole equals 34.09 grams. I do this calculation and I get 28.37 grams of H2S. But what does that mean? It means if all my iron chloride gets used up, this is how much H2S gets used up. But how much H2S did we start with? 52 grams of H2S available minus the 28.37 grams of H2S that gets used. H2S gets used equals the 23.63 grams of H2S left over. We figured it all out. In-depth problem. Okay, what's next? A whole nother problem. All right, I want you to look at this one and see what you can do with it. And we'll definitely do that one in class, okay? We got to move on to a new concept using a lot of the same stuff. Okay, the new concept is called percent yield. Any percent is always a part over total times 100. Okay, for percent yield, the part is the actual amount of product that you get in the lab. Actual amount of product. Actual product produced. Okay. Total, this bottom is a calculated amount from stoichiometry. Sometimes we call that a theoretical or expected yield. The total has to come from the limiting reactant. So, new definition, percent yields equals actual yields, actual amount of product, divided by theoretical amount of product, which is a yield, times 100. That's how you get a percent yield. So you might be saying to yourself, all right, what is this new thing, percent error? Well, if you know what you should get from stoich, that's theoretical yields, and you subtract off the actual yields, make sure you use absolute value, divide by the theoretical yields, which you should have gotten if everything worked perfectly, and then you multiply it times 100, then you're finding how far off you were. So percent yield is kind of like how on you were, like what you got on the test. Percent error is what you got wrong on the test. All right, that was an analogy. So we need to do that calculate the percent yield for this reaction. So they give us the 550 grams of this, okay, and then 305.1 grams of that. So we only know one reactant and we know the amount of product. So this number, 305.1, is the actual yield because they tell us how much product we get in the lab. So I tried to make this and this is how much I made. How much should I have made? So I have to take my reactant, C7H8, and you have to change it into product. So in order to change the chemical identity, you have to go through moles. Moles of C7H8. But those need to cancel and turn into moles of C7H7NO2. It's called p-nitrotoluene, organic molecule. Moles of C7H7NO2, 4 grams of C7H7NO2. All right, let's see what we got with the math. Okay, moles and grams. So anytime you have moles and grams, moles are 1, grams are 92.15. Okay. Anytime you have moles and moles, it's coefficients. So this has a coefficient of 1, and this has a coefficient of 1. Okay. Moles and grams again. Moles are number 1, and grams come from periodic table 137.15. Okay. Calculate. Hello, grams of C7H7NO2. That's called p-nitrotoluene. We find out that there should be 818.58 grams produced. Okay. So this is called a theoretical yield because did we do it in the lab? No. We did it using stoichiometry, and that's the maximum amount that could come out. And so now I have to do percent yield. So I have to do the 305.1 grams actually produced divided by the 818.58 grams that should have been produced. Multiply that by 100 to make it a percent. We get 37.27% yield. Okay. Right. Percent error, you can subtract that from 100, or you can just do 818.58 minus 305.1 divided by 818.58. Well, just don't forget to divide by or multiply by 100 so that you can get that. And so then I want you to predict what this should be. Okay, you tell me. Right? And just remember that your percent error tells you how wrong you were. Your percent yield tells you how right you were. Okay, let's look at another problem. It's a balanced equation. It says if 1.85 grams of this reacts, so that's a reactant, 512 grams form, so it's a product, what is the percent yield? Okay, before we can do a yield, they both have their products. I have to take the 1.85 grams of aluminum and change it into grams of copper. So I want you to try this problem. I'll let you know that the answer is 78.29%, and I want you to see if you can get that. So good luck, go get them, all right? And then we'll check it in class. All right, so a lot of stuff going on here, but remember that a limiting reactant gets used up and it controls the amount of products made. You don't have to leave it into moles, it can be grams, okay? So I don't know why I put that there, but limiting reactant can start out as grams and you can use it to figure out other stuff. The excess reactant is left over. It didn't get to react because there was nothing to react with. Okay, limiting reactant is used to calculate the amount of product expected in theory and the amount of excess needed, and then you can tell how much left over there is. Always go through moles. Okay, 3 exclamation points. Percent equals part over total, which is going to be actual yield over theoretical yield for us times 100. Okay, and the total comes from stoiching up the limiting reactant. All right, this had to be shorter than the last 2. Try a practice problem from the book, and we will practice until we get it. Peace out. Oh yeah, objectives. Seriously though, peace out.